Okay, I think we can start. I just realized, can someone go and switch off those lights? It is at the back side. Switch off the lights. I think the one having cross, I think that is the one. Okay, thank you. Uh, okay, so today we will continue with energy based model, but today will also be a transition to something else, and we'll see about that, right? But the discussion mostly will be around energy based models only. The problem, however, is that after today again there is a 1 week break because Tuesday it is holiday, uh, Mahavir Jayanti. Friday is Good Friday, so again holiday. Saturday I will not take class, even if there is. So which means we will next meet. I think obviously Monday we'll meet, but then the next Monday after that is when we will meet. Right. So there will be some uh, gap there as well. And the Saturdays that I'm not taking class, I will manage it by taking classes on uh, Monday during practicals. Okay. Obviously, I'll announce it over email, and then we will book some room here and we'll do it here, not there, because we'll record it also. So that is kind of the idea. Okay. Uh, okay. So with that background, let us come back and start for today. So if you remember, we were discussing and talking about energy-based models, right? We were talking about energy-based models. And in energy-based models, uh, our PDF that we are learning looks something like this. If you remember, it is equal to, remind me, 1 by z dot z theta, which is my partition function, and then exponential of f theta x, right? And then the advantage of this is the it is expressive, right? It is quite expressive, and that is the advantage. However, the disadvantages are, remind me, slow training and sampling, right? And these are aspects we have touched upon already, but we have not really solved either of this problem. We discuss how to train the model, we discuss how to sample from the model, but that does not solve the fact that training is slow. That does not solve the problem that sampling is slow. So remind me, how do we train this model in a vanilla sense? Can someone remind me how to train the model? Yes, contrastive divergence is fine, but what is contrastive divergence? What is the loss function in contrastive divergence? Let's say L of theta, let's say, which is my loss function, not the likelihood, obviously. In contrastive divergence, what is my loss function? You remember? You remember the philosophy of contrastive divergence? That training data at dose you will try to increase, whereas in any other sample, and that will be just one sample in the epoch, you will try to reduce. That was the philosophy. And anyways, with likelihood and all of those things, we actually showed that you can derive that. and we did derive that thing, right? But what did the loss function look like? It was f theta evaluated at the training point and minus f theta evaluated at some sample drawn from the distribution, and that we were trying to maximize. So negative of that is what we will try to minimize. So then my loss function is f theta xs minus f theta x train, right? Where, how do you get xs? Where xs is sampled from p theta of x, right? Where xs is basically a sample you are drawing from the distribution, correct? So let us write down the algorithm then. How do you think the algorithm will look like? Let's say just write down, let's try to write down just one epoch of the training process for energy based model with contrastive divergence. And let us try to see how does it look. And from there, let us try to see why is it expensive, right? So let us write down the training algorithm. So let me write down the training algorithm. And can you help me? How to proceed? What is the input? To start with, what are the inputs I have? Hmm? X trained, which is the data. So I have X train, then number of epoch, then some usual hyperparameters, learning rate, batch size, and those are the usual one. I'm not writing that, but you know that. There is learning rate, there is batch size. Uh, Obviously, f theta will have a network of its own. So f theta, how many hidden layer, how many nodes in hidden layer, and so on and so forth. You are aware of those, right? Uh, but we'll just write it for one epoch. So I'm not even going to write for I equal to 1 to ne. I'm not going to write that. I'm just going to write what you will do inside that for loop. That's all I'm going to write. Okay. Um, so when I say I'm going to write what you are going to do inside the for loop, that means I'm not even going to write that you need to initialize theta, for example, at the beginning. I mean, you need to initialize theta for the optimization, but I'm not even going to write that. I'm just going to write down what is happening inside the for loop. Because what is happening inside the for loop will be repeated again and again, and that will contribute to the cost ultimately, right? So inside the for loop, what will happen? See, what do you think? What will happen inside the for loop? There is some for loop that is going on here. Let's say, uh, what will happen inside the for loop? You need to sample excess. So let us. You will have to xs. You will sample from uh, exponents. Let's say p theta of x, which is proportional to exponential of f theta x. And just to be correct, I will write p theta I f theta I. What does theta I mean? That is the parameter value in that epoch, because theta is getting updated. So when you are in the ith step inside this training loop, parameters, since they are getting updated, so it will not be same when you are at the I plus 1th or n plus 1th step, right? So because it is getting updated, that's why I'm writing it. Okay. And how do you sample it? Hamiltonian Monte Carlo is generally not used. Unadjusted Langevin, right? or usual metropolis testing you can use. And this is just one sample, right? You might wonder that why is it expensive to sample one sample? It is expensive because you have to remember that first the burn-in period will come, which you have to ignore. Then you will have to see, okay, now it has stabilized, and then you will take that one sample. So one sample does not mean one step in your chain. One sample will probably mean thousands and one steps in your chain, but the first 1,000 are probably your burn-in period. Because it is like that, it's expensive. And this sample that you draw, you cannot use it in the next iteration. Because in the next iteration, what has changed? Theta is updated, the parameter is updated, which means the distribution has changed. You need to again run that chain from scratch in the next iteration. So that means if I am running it for 1,000 epoch, 1,000 times, and in sequential manner, I am doing this sampling. And because of that, it is very expensive. Clear why is it expensive? Right? So this is the step, obviously. So once you have this, you will do you will evaluate your loss function. Let's say what is happening. L theta you will calculate. Let's say, which is basically your f theta xs minus f theta xt. See, I am not writing x train, I am writing xt because xt is a batch you are taking from x train. X train is the total training samples, but when you train it, you will not use all the training samples. You will take a batch, and for that batch you will do, right? So that's why I'm using the term xt, which is basically a batch drawn from x train. And again, I'm now not writing theta I, I'm writing theta because the loss is function of theta, at least till now. I'll compute the gradient and then use that, evaluate that loss at, or gradient of loss at theta I to find out my theta I plus 1 or whatever, right? And then next step is theta I plus 1 is equal to theta I minus eta gradient with respect to theta L theta, and this you will evaluate at theta, right? And this will keep on, this will continue for the number of epochs, whatever you have decided, we have decided to run the code for, right? And because of this sampling step that is sitting inside the training loop, it's very expensive, right? So, and by the way, sampling itself is expensive always. And so sampling, you don't even need to, sampling will not do anything for now. So we'll only focus on the training part and see that if we can make the training at least more scalable than what this has to offer. Okay. Any questions? Because I've taken the minus sign already an L, so that's why. If you are not taking the minus sign, you will add a plus here. It will become gradient ascent in that case. Now, obviously, I'm written SGD here, but in reality, we'll probably using Adam, so the momentum terms will be added, and that's fine. Right? And that's not important at this point of time. So clear how energy-based models gets trained in the vanilla setup. So now, as I was saying, this is expensive, right? And this is the reason why it is expensive. Okay. And so the natural question to ask, and that is what we will discuss today, at least part of that. Uh, can we develop a sampling free scheme for training energy based model? Can we think of and develop a sampling free training scheme for energy based model? Okay. So can EBMs be trained without sampling? Okay. So our discussion in today's lecture will be around this question only. Okay. So to answer this question, I will like to introduce a new metric known as score. It is something known as score function. So let us introduce that score function. To be more specific, it was proposed by Stein. So we often call it Stein's score function. Stein. So Stein's score function or score function. Okay. What is a score function? Well, a score function is denoted as S. Uh, Let me write S. Um, Maybe for the energy based model only, let me write S theta is equal to gradient with respect to x, not with respect to theta, with respect to x. That is important. Log p theta x, because I will, or I can write S is equal to grad of x log of px, because I wrote theta on the right, I wrote theta on the left. I'm returning the term theta. The theta does not, I mean, theta is not needed for defining score, but I'm returning theta because ultimately I have to train for theta at some stage, and that is the reason I'm returning it, right? Okay, so this is known as score. Okay, this is known as score function. Uh, Let us do one thing. Let us take the Gaussian distribution, for example, and evaluate the score function for the Gaussian distribution. And let us take 1D Gaussian only. And let us see how the score function will look for a Gaussian. And from there, can we draw some conclusion? Can we draw some uh, observations? Let us see. Let us take the Gaussian distribution. So let's take the Gaussian. So what is the PDF of Gaussian? Someone remind me. F x x and 1D, 1 by sigma root 2 pi or root 2 pi sigma square, whatever you want to write. Then exponential of minus half x minus mu whole square by sigma, right? Um, so if that is the case, what is my score for this case? What is S? What is S for this case? So first you will take log and then take derivative of that log with respect to x. So if I take log, denominator that you are seeing, that will become minus log of sigma root 2 pi, right? And the remaining term will be log and exponential will cancel out. You will end up with minus half x minus mu whole square by sigma square. And then you will take derivative with respect to x. The denominator which was there will become 0, it's not a function of x. So what you will be end up with is the derivative of the term inside, which will be x minus mu by sigma square. That's what you will get, right? So S is equal to, let me write down these steps, whatever I said, d dx minus log sigma minus log root 2 pi. Log and exponential will cancel out, so minus half x minus mu whole square by sigma square. This is what I will get, right? And that is equal to, so this will tell me that s is equal to, s is equal to, um, so there is minus half, the square 2 will come, so 2 and half will cancel out, the minus will stay, so I will get minus x minus mu by sigma square. So this is my score for the Gaussian, right? So, and what was the PDF? The PDF was fxx. Now the PDF you can think of it as likelihood also, and Gaussian likelihood, whereas this is 4. So now tell me, if I compare 1 and 2, where 1 is this one, let's say, this is 1, let's say, just for comparison, and the box is 2. So if I compare the PDF or likelihood with the score, can you tell me what are the few things that you observe here? Few things, and some of those things can be, might be useful, some of those might not be useful, and that is absolutely fine. But can you tell me what you can observe generically without any objective or goal? You look into equation 1 and 2, compare, what do you observe? So I'll simplify that. The score function is simpler than the PDF. Things get cancelled out, it is much simpler. Huh? The score function is much simpler than the PDF. Everyone agrees? Because exponential log cancels out, take derivative, so even the power goes down and all of those things. So let me write it down. Observations. Uh, Observations. One is score is relatively simpler. This is the obvious one. Anything else you see between the two? Anything else do you see between the two? The score that you see in equation 2 and the PDF that you see in equation 1, is there some other observations you have? What was sigma root 2 pi? Partition function? Where is the sigma root 2 pi in case of 4? It does not exist. Partition function is never a function of x. It is a function of theta, it is a constant, but it is not a function of x. And because it is not a function of x, when you take log and then take derivative with respect to x, that vanishes. Which means code is not a function of the partition function. So that is very important for us because our main bottleneck was the partition function in case of energy based model. With this code, we are eliminating that bottleneck. If we can use the score somehow, I don't know how, but somehow, we can use the score to train our model. Our headache about the partition function is now out of the picture, right? So the score function do not have the partition function. That is the second observation. Score is not a function of, instead of writing partition function, I'm writing z. And we know z is the partition function, right? I'm writing z, z, whatever you call it, but I mean that's the partition function. It's not a function of the partition function. And this is very important for us in the context of EBM. There is one more observation, but that is not obvious. Uh, and that is not valid even for this two expression. That will be valid if you take, so now I'm not going to write it, But imagine that this Gaussian PDF I took is a multivariate Gaussian. How will it look if it is multivariate Gaussian? So there will be root 2 pi to the power n by minus n by 2, determinant of sigma inverse, exponential of minus half, x minus mu transpose, sigma inverse, x minus mu. That's how it will look, right? We find the score function of that. So how will the score function look for that? First percent will go to 0, exponential and log will cancel out. So now the derivative, so will be x minus sigma multiplied by x minus mu, sigma inverse multiplied by x minus mu, right? That's what you will get, right? Now compare the two. One more observation is important. Can you tell me what is the other observation? What was the output of the PDF? Even though x was a vector, what was the output of the PDF? Scalar. PDF is a, or likelihood is a scalar valued function. You give a vector, output is scalar. Likelihood of PDF is a scalar valued function. Score function is a vector valued function. So it is x minus mu, x will become vector, mu will become vector, sigma inverse, whatever. So now what we have is a vector valued function instead of a scalar valued function. That is the third observation. That is the important observation, obviously. It was not valid in the 1D case, obviously, but that is a valid observation, right? So the third one is score is vector valued. Okay, nothing. You should know that. Not everything need not have a significance. Okay. Score has a significance, but score being vector valued is an observation. Okay. There is one more significance. Obviously, you have to use matrix calculus or vector calculus. So calculus part might become a little bit more trickier, right? Okay. Now, physically, what is score? What does it even mean, right? So let us try to understand that, or let me try to explain that in a graphical way. Okay. Suppose I have a distribution. Uh, this is not a distribution; it's a domain. And let me draw the distribution in a contour manner, right? It will be easier for me. So let's say there is one mode here, uh, one mode here, and maybe one mode here. Okay. This is the contour lines I'm trying to plot. Obviously, I'm drawing it very bad, but that's okay. And then, okay, something like that. Let's say the contour is something like that. Even in this bad drawing, you can see that there are three modes, and that's all that matters. Anything else does not matter, at least till now, right? You can see this is the contour, and it's some distribution, some complex distribution, maybe mixture of Gaussian, I don't know, uh, which has three modes. And what is mode? The point having the highest probability mass or frequency, density, whatever you want to call it. Right? That's what mode is. Now, for Gaussian, mean and mode are same, but not for everyone. This is your PDF, right? Even if it is 2D space, you can draw a single contour. It will give a single value. That's a scalar valued function, and that's why I can draw like this. Correct? Now, if I try to draw the core function over that, how will it look? How do you think it will look? First of all, the score is a vector valued function, so it's a vector. It will be a vector, right? And if you look at the resultant vector, it will have some magnitude and some direction, right? Let's not worry about the magnitude. I mean, you can always find it out. But what do you think the direction will be of the vector field? Towards the mode maxima, right? So from each point, whatever is the minimum one, it will look like that. If you draw it over this, uh, so from here, it will probably point like this, right? From here, point like this. From here, point like this. The magnitudes, the far it is, the larger it will be. Okay. Here it will try to point like this. And similarly, I mean, I'm not drawing everything, but you can understand what the message you are, I think, is quite clear. So that's what physically a core function is. It's a vector field, right? Uh, if you think of PDF as some potential energy kind of thing, it's a gradient of that energy, right? I mean, something like that, gradient of the potential, and it will point towards the mode, and that is kind of obvious actually, but yes, right? That's what it is physically. But in practice, we will like to use core function to train our energy based model. And that is where we started. And we train energy based model without the need for sampling. Sampling was needed because the partition function was not known. So we started talking about core function. So now the question boils down to, can we use core function to train our energy based model? Can we think of any metric, a metric that will allow us to use the score function to train our energy based model, right? So let us focus on that aspect now. You have some idea of what the score is. You have some idea of the difference between a score and a likelihood. So now the question is, instead of likelihood, can I use score to train my model, right? Okay. So now with that, let me separate it out. So can score function be used to train a model? I mean, in our case, that model is EVM, obviously, but my question can be more generic. It need not be even EVM. Can it be used for train some model, right? So there is something known as Fisher divergence. Like the Kullback-Leibler divergence, there is also something known as the Fisher divergence. Fisher was a very famous statistician, and he came up with the Fisher divergence, right? So let's look at how the Fisher divergence looks like. For any divergence, what do you need? Two PDFs. The divergence generally talks about distance between two PDFs, right? Right. So if it is divergence between two PDFs, so P and Q. So P is a PDF, Q is a PDF. I'm looking at divergence between the two PDFs, but not the KL divergence, but the Fisher's divergence. So how does it look? It looks something like integration of P, okay, integration over P So the first term, the integration is over that. And then you have norm of gradient of x log p minus gradient of x of log q, and the norm is a second order norm, I mean L2 norm, uh, dx. Okay. Now x is there because p is actually a function of x. I have not written that. Q is also a function of x. I have not written that. Right? This is your Fisher divergence. It is very similar to the KL divergence actually. What is the difference between KL divergence and this one? KL divergence was log p by q. Here log of gradient of p by gradient of q. So p by q is replaced by gradient. Correct? That is the only difference. It is uh, otherwise very similar to KL divergence, and again it is not symmetric. P and Q change, you will get different things, right? So it's again not symmetric. So it's not a distance. Distance are supposed to be distance metrics are supposed to be symmetric. It's a divergence. It's not symmetric. It's some kind of difference or distance metric, but not distance exactly, but in a very loose sense. So some difference between two PDFs. So basically, what is it saying? It is saying if the gradient of the PDF matches for two different PDFs, then those two PDFs are probably same. If the log gradient of the two PDFs matches, then those PDFs are same. This is the hypothesis we take that gives rise to this Fisher divergence. If you take the divergence that if obviously this is expectation also, but I did not use the term expectation. So KL divergence, what is the philosophy? The expectation of the difference of the logs of the PDFs is minimized. That means the two PDFs are coming closer to each other. Here it is, if expectation of log of the gradient of PDFs, two PDFs are minimized, that means the two PDFs are coming closer to each other. And that is 0, then they are identical. Right? So this is known as the Fisher divergence. Any question? No, it is not. I mean, other means others. That is also not symmetric. This is also not symmetric. So KL divergence and this one both are not symmetric. Oh, by the way, before I forget, I'll come back to that. So actually, I should also write a half here. Okay. In many places, there is a half outside. I mean, it really does not matter in the bigger scheme of things, but to be complete, I'm using that. Right? So yeah. So what you were saying is why? No, you cannot. You can use either. None is perfect. Okay. You can use either. One way to decide it is that if calculation is simplified in one of them. And you will see very soon that there are some challenges we will face with this, uh, some cons obviously, and there are other things we will face. So let us discuss this, and you will. I think some of those questions will be answered. I don't want to jump the gun and answer those beforehand because that might make sense to you, but others might get confused. So let us go step by step. So you will see the limitations and how we address those uh, in a short way. So this is the Fisher divergence, right? And clearly you can see there is a log of gradient of log is hitting. So if I use this, the score function will be used. And if I use the score function, the z will stop mattering to me. So this seems like a good possibility. So now, if this seems like a good possibility, let us try to use it for EVM. And let us see if we can, or maybe we can't. I don't know. So let me call it equation 3. I will refer to it actually. So So in EVM, What do we have? We want, or rather what we want, p theta of x should match or be as close as possible uh, p theta of x should match p theta of x, right? This is what we want. That means I can think of using Fisher's divergence between these two things, right? So using equation 3, Fisher divergence between p data and p theta. Again, it's a function of x. I'm not writing it, but how will it look? Maybe equation 3, let me simplify a little bit more. This is equal to half of expectation, where x is drawn from p right? It is an expectation. So what is this equal to then? Expectation x drawn from p data. This is not a problem. We have Trinity to start with, and then inside I have the L2 of gradient of x of log of p theta minus gradient of x of log of p theta. Both are function of x. Again, I'm not writing it. Now, can you use it? Can you use it for EVM, at least in this form? Do you see any problem, or do you think it is fine? What do you want to learn? P theta. What is this function of? And that is something inside a square. So it's not like one term you can ignore. How will you use it? Samples I'm already taking. It is sitting outside. But what about the gradient of log of p theta? See what the problem is? There is a gradient of log of p theta sitting inside a norm, not even separate that you can ignore it. Hmm? Uh, so gradient of the target distribution that I want to learn, not even the target, the gradient of that, and that is to be known for using this. If I know this, why will I use this? If I know this, I don't need a generative model, right? So that is the main thing I want to learn, and it is a function of that. So clearly, in this form, at least I cannot use it. We need to do some simplification, right? And we will do some simplification by using integration by parts. Okay, so let us see what simplification we can do, but we definitely need to do some simplification. But the simplification I will not do in the vector form, I will do it in the scalar form. Okay, to make my life easier. Vector form I will give one of the homework to make your life difficult. Anyways, uh, or practical maybe. Yeah. So this, oh, by the way, I have not written the half. You should write it. Right? Cannot be used in practice as gradient of x log of p theta is unknown, right? This cannot be used in practice because this one is unknown. We need to do some mathematical operation to at least try and remove or approximate or do something about that gradient of x of p theta. So we use integration by parts. Okay. So let us see univariate case. How will it look in the univariate case? So Fisher divergence between p data and p theta, right? P data and p theta, yes, will look or will take the following form. But remember, it is now univariate, so things will be simpler. Expectation x from p theta, where x is a scalar, uh, and then inside, what will I have? Square, right? It will become square. It is delta x log of p data x minus delta x log of p theta x square, right? Now you tell me, and this is a very simplification, I should have done it earlier, but I did not do it. So you people do it and tell me, what is this term equal to in case of EVM? Gradient of x log of p theta x, what is it equal to in case of EVM, not in general? Do the calculation. You know what is log of p theta. What is log of p theta in EVM? F theta, right? It is exponential of f theta by z theta. If you take a log, it is f theta minus log of z theta, a gradient of that. So it is that, right? It will be gradient of x of f theta. Where are you getting Gaussian? Okay, this is clear for everyone. Anyone is there who does not follow what is happening? Everyone follows? It's very simple. Just take the PDF of EVM and just take a log and then take a derivative. That's all that is, right? Okay. Okay. So this is what I have. What I am going to do is that I said integration by parts. Where is the integration? There is no integration until and unless I write the expectation as an integration. So let me write that. So let me write the expectation as an integration. This is equal to integration p theta x. And now there is a minus b whole square kind of term, right? So I will open it as a square plus b square minus 2ab. The half also I am forgetting. Let me write that half. I am forgetting it too long. Okay. So a square plus b square minus 2ab. What is a square? Grad of x log p theta of x square of that. This is my first term, right? What is my second term? B square. The second term will be gradient of x. I will write f theta x square and then minus 2ab minus, so 2 gradient of x log of p theta gradient of, I am not writing the, let me write the x, and then gradient of x f theta x, and then there is a dx. Okay. So now there is no whole square kind of thing. I have separated the whole square into 3 terms. That means if I open that curly bracket, I can get 3 separate terms. So let me write down those 3 terms separately, and you will help me on that. So what is the first term? Tell me what the first term is. Wait. Half integration of p theta of x, then gradient of log of p theta x. This is my first term, right? Everyone follows? Just have opened the bracket, nothing else. What is the second term? Wait, change color. The second term will also have half. Integration of p theta never changes. And then inside I have gradient of x f theta, right? Square dx. Everyone follows? The third term, so minus half and 2 will cancel out, so minus nothing. Minus integration of, tell me, p theta of x multiplied by gradient of x log p theta of x multiplied by x f theta of x dx. Is it clear? Yep, it's very simple. It's lengthy, but it's not difficult. It's very simple, right? Now we will go term by term. Okay. Let us look at the first term. What do you observe about the first term? What do you observe about the first term which is in red? Independent of theta. If I'm optimizing for theta, that will not matter. It is constant when it comes to theta. So this is not a function of theta. So ultimately this can be treated as a constant. And in the gradient, that term will not appear. Okay. Second term, what do you observe? This is when I will give the answer, it will be very obvious, but your mind might not take you there directly. Second term, what do you observe? Do you observe anything about the second term, anything special about the second term in the context of what we have discussed earlier? That is the clue. The second term is not a function of p theta, which was our bottleneck. The second term is independent of p theta, which means the second term is not our bottleneck. Our bottleneck is p theta. P theta is something we do not know, right? Second term, is there any p theta? There is the expectation obviously, but expectation will sample. Second term, if you write in terms of expectation, inside the expectation there is no p theta, which means if you do sampling and represent that expectation with the training samples, That is not our headache, right? The second term is this is equal to expectation x from p theta gradient of x f theta x uh, square, right? So this is not our headache, because you can understand that I have the sample x from as in form of my training samples. I'll use those samples and evaluate this. And evaluating this thing, what is inside the bracket, is not at all a headache. That's my neural network. And I have to take gradient. I will use automatic differentiation. Right? Clear? So what is the bottleneck now? The third term. The third term is having p theta and p theta together. Right? So in the third term also there is a trick. Let's see. This, if I do the gradient, what will I get? There's a gradient of log of p theta. Let's do the gradient. What will I get? 1 by p theta. Let me write it down. 1 by p theta, then multiplied by x p theta. So this and this cancels out, right? But the gradient of p theta is still there. But the good thing is now there are two terms inside the integral. Previously there were three terms inside the integral, right? Now with this cancelling out things, I now am left with two terms. And I said I will use integration by parts. With two terms, now integration by parts is in the game, right? So now we will focus on the last term after simplification, which is cancelling out p theta, and now talk about integration by parts, right? So the third term is the bottleneck, right? The third term is the bottleneck. So what we will do is using integration by parts. Okay. So suppose I have a integration by parts, uh, which is something like this: u v dash. Okay. What is the integration by parts formula for this? Remind me, I forgot. Remind me. Yeah, that's how the way I have written. Same. That will decide. In this case, what will be the? In this case, uv, correct? Uv minus integration of u dash v, right? So you can see integration by parts allows us in this form at least to exchange the derivative. Derivative was in v dash, but with this it goes to u dash, right? We'll do that. Okay, we'll do that because our bottleneck is gradient of x with respect to log of p theta. So that gradient is like u dash. That will eliminate. We eliminate, now we are in the game with our expectation operation. So the training samples will be used. So you can imagine what we are trying to do, right? So this we will use. So this, let me box it. This is, everyone knows. Although maybe this is not the form that we usually write, but this is obvious, right? We write uv, not uv dash, but that's okay. So now let me first write down the term that we already have without any. We have what? Integration of gradient of x log p theta of x. Now I'm not simplifying yet. And then gradient of x f theta of x dx, right? Gradient of x f theta is not our headache. I can take as many derivatives as I want as long as there are some constants that are satisfied. Log will not be there. Correct, correct, correct. Thank you. What happened? I'll write again. No, you cannot undo here. I'll write, don't worry. We use integration viper, so IVP. Okay. So now I'll write like this. IVP, and when we use IVP, what do I have? I have integration of gradient of x, log is not there, so I'll not make that mistake again. P theta of x, uh, gradient of x, f theta of x dx. Okay. And what we will do is as follow. You know why it happened? It happened because this was close to this and I was trying to use the mouse pad. Now I'll hold it in my left hand. Uh, yes. So let me change the color. So now what I'm saying is this one. This is my u dash or v dash. This is my v dash. Right? And this is my u. I wrote u v dash, right? So then what will I get? Using this is equal to this is equal to, there will be two terms of this is the first term. Let me tell me what is the first term. P theta x x grad of x f theta x, and this you will evaluate at where? Integration, right? The integration limit will come. Expectation is I am writing integration, but it is integration minus infinite to plus infinite. You have to keep that in mind, right? Okay. Second term, how will it look? Wait. Uh, this was my first term. So now minus, right? Integration p theta of x Hessian right? Clear? Everyone follows? Tell me what is the first term equal to? Under some assumption. Under some very relaxed, very lenient assumption. There has to be some assumption. There are exceptions to that, but in general, what do you think the first term that is in 0? Why? Generally, at the boundary, probability is very less, right? Any probability you think they are having, but at the boundary, they generally go to 0 in most cases. At the both end, they are 0, and you are taking the difference, 0 minus 0 will go to 0. Obviously, you can always come up with a case, no, I have a direct delta at the boundary. Then that's a special case you are creating, right? But that does not happen. And even in that case, you can say that it's minus infinite. It's infinite literally. Wherever the direct delta is, you can say, no, that is not infinite. I will go much bigger and that is infinite, then it is again 0. So it's a very uh, reasonable assumption, I will say, right? This term is equal to 0. Okay. And what is the second term equal to? The second term is equal to expectation x from p theta grad x square f theta x, right? Okay. So then now with all of this, what is my Fisher divergence now looks like? So therefore, finally, therefore, Fisher divergence between p data and p theta is equal to, the first term is a constant, right? The second term is equal to, second term is not minus. Where is the second term? I lost it. Here, expectation of, and there is a half outside. Don't forget. Okay. So this is equal to half expectation x coming from p theta, and then inside it is gradient of x f theta x square, right? And then the third term is equal to minus, and minus becomes plus. This is a minus sign there, and there is a minus sign there. So minus and minus will become plus. So plus expectation of x from p theta gradient of x square f theta x, and if I combine these two, what will I get? Expectation is common in both, so uh, gradient of x square f theta x plus half uh, gradient of x f theta x. And now you have a loss function that you can evaluate, because it is only in terms of f theta uh, and gradient of f theta, Hessian of f theta, which you can easily calculate, at least in theory. Uh, you have training samples that you will use to express the expectation. You have a proper training objective. This objective is to be maximized, negative of this is to be minimized, but you have a proper training objective finally, right? Clear? Hmm? This is to be minimized. Yes, yes, right. Because it is divergence. Correct. This is to be minimized. Exactly. So this is to be minimized, right? Clear? Now, coming back to the question you asked earlier, why do you think it is not used that often? What is the bottleneck? Hessian calculation is very expensive. Calculating Hessian is non-trivial. So that creates a major bottleneck, right? Also, the architecture is slightly limited with this. You have to use an activation function that is at least twice differentiable. If you do not have a skip connection or something like that, otherwise this term will go to 0, and that will create problem with training your model. So that also brings some architectural constraint for this, which people often ignore, but you have to be careful that you should be able to differentiate with respect to x twice, at least, if not more. More is better because then it is function of x after, even after you have differentiated it. You can, but that is expensive. Hessian calculation is expensive. Architecture choice is limited. some of the choices goes out of the window. That is the issue with the architecture design. And Hessian you can calculate. You have to use our automatic differentiation. But Hessian calculation is expensive, particularly for large network. Because remember, it is not a physics informed network where x is 1, 2, or 3 dimensions. Think about a image. Your x is 1000 cross 1000. What will be the dimension of this? You can imagine, right? So it will be huge. It will be 1000 cross 1000 cross 1000 cross 1000. That is what you are dealing with. It becomes very expensive. Obviously, number of data is also there, so that is also there. So you have to do some tricks there, which we'll talk later. But there are clear problems with this. This is obviously that is the trade-off, right? And that is the trade-off even in optimization. In optimization, when you do Hessian, that is more accurate, but more expensive. So accuracy comes at a cost. No free lunch, right? No free lunch theorem is there. So it's that it is more expensive, obviously, but nothing is free. And obviously, right? Gradient matching will give you more information than just matching the original PDF, and that's what you see here, right? So now finally, and I will stop with this. I will not go ahead. So I'll just write the algorithm and stop. So how will the algorithm look like? Whether this is known as code matching. This is known as code matching because you are taking the score and matching it with the score of the data in some sense because Fisher is like two scores, right? This is known as code matching. To conclude today's lecture, so one is you have training data is given, input is like expand, select batches, batch, compute loss using equation 4. Let me number it. This is my equation 4. That's all right. You have the training data, you will select a batch. For that batch data, you will use equation 4 to compute the loss. And then with that, you will compute the gradient. Okay, one thing I wrote wrong. Do you know what is wrong? Either plus C or I have to write proportional. Also here, right? That doesn't matter in the bigger scheme of things. When you take gradient, it goes away, but in general. Okay, so this is known as code matching. It's a energy based model. Code matching is the training algorithm. Previous one was contrastive divergence. Okay, obviously you can understand this is much simpler than that one. Here the main bottleneck will be the Hessian calculation, and there are some more efficient ways of doing that, which we'll talk later. Maybe next lecture or next to next lecture we'll talk about that. Okay. And with this code into picture, you know that I don't know. I mean, you probably don't know. Not all of you definitely don't know that code is what is used for training diffusion as well. And matching has already come, so flow matching will also have some relation to this very soon. Okay. But uh, it can be used. I will not say it is used. It can be used. Let's put it that way. Okay. So actually, the code matching, I think, yeah. So after this, there will come noise contrast and from there will go. But yes, this can be used for training continuous normalizing. Right? It's a generalized idea. It has nothing to do with this. It's a divergence, right? And it was not proposed for let's say energy based model. It was proposed much earlier. Energy-based model used this. Fisher came much earlier, right? Fisher information criteria, Fisher matrix, so many things are there. Okay. Good question. There is no answer. Someone thought that I will call it a score. Called it. Okay. There is no answer. I searched for it actually. That why is it called score? Why not something else? Because Stein thought that that's a smaller name. No, nothing like that. It has nothing to do with that. Stein thought score is a good name. Small, good name. I could not find any reason. To be very honest, I searched for it. Because code has a meaning, right? But I could not find anything. Okay, thank you.